In duplex systems, there are multiple methods for connecting to the grounding electrode conductor, or GEC. Firstly, the ground rod can be connected to the neutral at the duplex meter base. The grounding electrode conductor is then run from the water main to one panelboard neutral bus bar. The other panelboard has a short length of copper wire brought out from the neutral bus bar and split bolted to the grounding electrode conductor going to the water main. Secondly, the same configuration can be used, but a compression connector is used for the connection instead of a split bolt. Thirdly, separate grounding electrode conductors can be run from each panelboard to the water mains. In all these scenarios, the grounding electrode conductor connects to both water mains. The only reversible connection required is where a ground rod is connected to the grounding electrode conductor underground, buried within 1 foot of dirt. This aims to make this connection physically difficult without excavation. There isn't a broad national electrical code requirement mandating a compression connector for the tap to the other panel. This requirement is at the discretion of the local authority having jurisdiction, or OJ. Considering disconnecting the grounding electrode conductor, there's not a method that would prevent someone from doing so after it leaves the house. The National Electrical Code does not have a requirement for a homeowner to disconnect the grounding electrode conductor at the water main. If an irreversible connection to a supplemental ground rod is desired, a separate ground rod for the grounding electrode conductor can be installed. The grounding electrode conductor can be cut and placed 1 foot underground inside a short section of 4-inch conduit. Then drive the ground rod into the piece of conduit, and if a cap is placed on it, it will be all but impossible to disconnect the grounding electrode conductor from the supplemental ground rod. Regarding grounding electrode conductor sizing, the size of the grounding electrode conductor is based on the size of the service entrance conductors. Refer to National Electrical Code Table 250.66 to determine the correct grounding electrode conductor size. It is important to ensure that the grounding electrode conductor is properly sized to provide an effective ground fault current path. In addition to the water pipe and ground rod electrodes, other types of grounding electrodes are also permitted by the National Electrical Code. These include concrete encased electrodes, ground rings, and other listed electrodes. It is important to select the appropriate type of grounding electrode for the specific application and soil conditions. When installing grounding electrodes, it is important to comply with the requirements of the National Electrical Code. This includes ensuring that the electrodes are installed at the correct depth and spacing. It is also important to protect the electrodes from physical damage and corrosion. Proper grounding is essential for electrical safety. It helps to protect people from electric shock and to prevent damage to electrical equipment. By following the requirements of the National Electrical Code, it is possible to ensure that electrical systems are properly grounded and safe. There are many different types of grounding and bonding conductors used in electrical systems. Grounding conductors are used to connect non-current carrying metal parts of equipment to the grounding electrode system. Bonding conductors are used to connect different metal parts of equipment together to create a low impedance path for fault current. The National Electrical Code specifies the minimum size of grounding and bonding conductors based on the size of the overcurrent protection device. It is important to select the correct size of grounding and bonding conductors to ensure that they can safely carry the maximum fault current. Grounding and bonding conductors must be installed in a neat and workmanlike manner. They must be protected from physical damage and corrosion. They must also be securely fastened to the equipment and to the grounding electrode system. Proper grounding and bonding are essential for electrical safety. It helps to protect people from electric shock and to prevent damage to electrical equipment. By following the requirements of the National Electrical Code, it is possible to ensure that electrical systems are properly grounded and bonded. There are many different types of electrical panels used in electrical systems. Electrical panels are used to distribute electrical power to different circuits in a building. They also contain overcurrent protection devices, such as circuit breakers or fuses, to protect the circuits from overloads and short circuits. Electrical panels must be installed in a location that is readily accessible and free from obstructions. They must also be protected from physical damage and corrosion. Electrical panels must be properly grounded and bonded to ensure electrical safety. The National Electrical Code specifies the requirements for the installation of electrical panels. It is important to comply with these requirements to ensure that electrical panels are installed safely and correctly. There are many different types of wiring methods used in electrical systems. Wiring methods are the way in which electrical conductors are installed and protected. Common wiring methods include conduit, cable, and wire. Conduit is a rigid metal or plastic tube that is used to protect electrical conductors. Cable is a flexible assembly of electrical conductors that is used to transmit electrical power. Wire is a single electrical conductor that is used to connect electrical devices. The National Electrical Code specifies the requirements for the installation of wiring methods. It is important to comply with these requirements to ensure that wiring methods are installed safely and correctly. There are many different types of electrical boxes used in electrical systems. Electrical boxes are used to enclose electrical connections and to provide a mounting point for electrical devices. Common types of electrical boxes include metal boxes, plastic boxes, and weatherproof boxes. Electrical boxes must be installed in a location that is readily accessible and free from obstructions. They must also be protected from physical damage and corrosion. Electrical boxes must be properly grounded and bonded to ensure electrical safety. The National Electrical Code specifies the requirements for the installation of electrical boxes. It is important to comply with these requirements to ensure that electrical boxes are installed safely and correctly. There are many different types of electrical devices used in electrical systems. Electrical devices are used to control and use electrical power. Common types of electrical devices include switches, receptacles, and lighting fixtures. Electrical devices must be installed in a location that is readily accessible and free from obstructions. They must also be protected from physical damage and corrosion. Electrical devices must be properly grounded and bonded to ensure electrical safety. The National Electrical Code specifies the requirements for the installation of electrical devices. It is important to comply with these requirements to ensure that electrical devices are installed safely and correctly. There are many different types of electrical systems used in buildings. Electrical systems are used to provide electrical power to different parts of a building. Common types of electrical systems include residential electrical systems, commercial electrical systems, and industrial electrical systems. Electrical systems must be designed and installed by qualified electricians. They must be properly grounded and bonded to ensure electrical safety. Electrical systems must also be inspected and tested to ensure that they are safe and operating correctly. The National Electrical Code specifies the requirements for the design and installation of electrical systems. It is important to comply with these requirements to ensure that electrical systems are safe and reliable. There are many different types of electrical hazards that can occur in electrical systems. Electrical hazards can cause electric shock, burns, and other injuries. Common types of electrical hazards include contact with live electrical conductors, ground faults, and arc flashes. It is important to be aware of the electrical hazards that can occur in electrical systems and to take precautions to avoid them. Precautions include wearing personal protective equipment such as gloves and safety glasses, and energizing electrical equipment before working on it. The National Electrical Code specifies the requirements for electrical safety. It is important to comply with these requirements to ensure that electrical systems are safe and prevent electrical hazards. Electrical safety is a critical aspect of working with and around electrical systems. Understanding basic electrical principles, adhering to safety guidelines, and using appropriate personal protective equipment are crucial for preventing electrical accidents. One of the fundamental concepts in electrical safety is understanding the path of electricity. Electricity always seeks the path of least resistance to return to its source. If a person becomes part of this path, they can experience an electric shock, which can range from a mild tingle to a fatal event. To prevent electrical shock, it is essential to avoid contact with energized electrical components. This can be achieved by de-energizing equipment before working on it using insulated tools and maintaining a safe distance from exposed conductors. Grounding is another important aspect of electrical safety. Grounding provides a low resistance path for fault current to flow back to the source, which helps to trip over current protection devices, such as circuit breakers or fuses, and de-energize the circuit. Proper grounding is essential for preventing electrical shock and fire hazards. It is important to ensure that all electrical equipment is properly grounded and that the grounding system is regularly inspected and maintained. Personal protective equipment, or PPE, is an important line of defense against electrical hazards. PPE includes items such as insulated gloves, safety glasses, and arc-rated clothing. Insulated gloves protect the hands from electrical shock when working with energized equipment. Safety glasses protect the eyes from arc flash and other electrical hazards. Arc-rated clothing protects the body from burns in the event of an arc flash. Arc flash is a dangerous phenomenon that can occur when there is a short circuit in an electrical system. Arc flash can produce extremely high temperatures, intense light, and a pressure wave that can cause serious injuries or death. To protect against arc flash hazards, it is important to conduct an arc flash risk assessment and implement appropriate safety measures. These measures may include energizing equipment before working on it using arc-rated PPE and installing arc flash barriers. Lockout-tagout, or LOTO, is a safety procedure used to prevent accidental energization of equipment during maintenance or repair. LOTO involves isolating the equipment from its energy source and placing a lock and tag on the energy isolating device. The lock and tag indicate that the equipment is de-energized and should not be operated until the lock and tag are removed by the authorized person. LOTO is an essential safety procedure for preventing electrical accidents. In addition to these safety practices, it is important to follow the requirements of the National Electrical Code and other applicable safety standards. The National Electrical Code provides detailed guidelines for the safe installation and operation of electrical systems. By following these safety practices and complying with applicable safety standards, it is possible to significantly reduce the risk of electrical accidents and ensure a safe working environment. Electrical systems are designed to operate within specific voltage and current ranges. Overvoltage and overcurrent conditions can damage equipment and create safety hazards. Overvoltage can occur due to a variety of factors, such as lightning strikes, utility switching surges, and equipment malfunctions. Overvoltage can damage sensitive electronic components and cause insulation breakdown. Overcurrent can occur due to overloads, short circuits, and ground faults. Overcurrent can overheat conductors and equipment, leading to insulation damage, fire hazards, and equipment failure. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when an overcurrent condition occurs. These devices protect electrical systems from damage and prevent safety hazards. Circuit breakers are resettable overcurrent protection devices that can be tripped manually or automatically. Fuses are non-resettable overcurrent protection devices that must be replaced after they have blown. A selection of overcurrent protection devices is based on the ampacity of the conductors and the rating of the equipment being protected. It is important to select the correct size of overcurrent protection device to ensure that it will provide adequate protection without nuisance tripping. In addition to overcurrent protection devices, surge protective devices, or SPDs, are used to protect electrical systems from overvoltage conditions. SPD diverts surge current to ground, preventing it from damaging sensitive electronic equipment. SPD are typically installed at the service entrance of a building and at individual pieces of equipment that are particularly sensitive to overvoltage. It is important to select SPD with an appropriate voltage rating and surge current capacity. Regular inspection and maintenance of electrical systems are essential for preventing overvoltage and overcurrent conditions. Inspections can identify potential problems such as loose connections, damaged insulation, and overloaded circuits. Maintenance activities such as tightening connections, replacing worn components, and cleaning equipment can help to prevent overvoltage and overcurrent conditions and ensure the safer and reliable operation of electrical systems. Troubleshooting electrical problems requires a systematic approach to identify the cause of the problem and implement the appropriate solution. Common electrical problems include power outages, trip circuit breakers, short circuits, and ground faults. When troubleshooting electrical problems, it is important to follow safety precautions to avoid electrical shock and other hazards. These precautions include energizing the circuit before working on it, using insulated tools, and wearing appropriate personal protective equipment. A multimeter is an essential tool for troubleshooting electrical problems. A multimeter can be used to measure voltage, current, resistance, and continuity. These measurements can help to identify the cause of the problem. When troubleshooting a power outage, the first step is to check the circuit breakers or fuses to see if any have tripped or blown. If a circuit breaker has tripped, it can be reset after the cause of the overload or short circuit has been identified and corrected. If a fuse has blown, it must be replaced with a fuse of the same rating. If all of the circuit breakers and fuses are in good condition, the next step is to check the power supply to the building. This may involve contacting the utility company to report the outage. When troubleshooting a short circuit or ground fault, it is important to identify the location of the fault. This can be done by visually inspecting the wiring and equipment for damage. A multimeter can also be used to test for continuity between conductors and ground. Once the location of the fault has been identified, the wiring or equipment must be repaired or replaced. It is important to follow the requirements of the National Electrical Code when making electrical repairs. Electrical maintenance is an important part of ensuring the safe and reliable operation of electrical systems. Regular maintenance can help to prevent electrical problems and extend the life of electrical equipment. Common electrical maintenance activities include inspecting wiring and equipment for damage, tightening connections, cleaning equipment, and testing overcurrent protection devices. Inspecting wiring and equipment for damage can help to identify potential problems such as frayed wires, cracked insulation, and corroded connections. These problems can be corrected before they lead to more serious issues. Tightening connections can help to prevent loose connections, which can cause overheating and electrical fires. Cleaning equipment can help to remove dust and dirt, which can insulate components and cause them to overheat. Testing overcurrent protection devices can help to ensure that they are functioning properly and will protect the electrical system from overloads and short circuits. Electrical repairs should only be performed by qualified electricians. Electrical repairs can be dangerous if not performed correctly. It is important to follow the requirements of the National Electrical Code when making electrical repairs. Before performing any electrical repairs, it is important to de-energize the circuit and verify that it is de-energized with a multimeter. This will help to prevent electrical shock. When making electrical repairs, it is important to use the correct tools and materials. This will help to ensure that the repairs are performed correctly and safely. After making electrical repairs, it is important to test the circuit to ensure that it is functioning properly. This can be done with a multimeter. Grounding electrode conductors play a vital role in electrical safety by providing a low impedance path for fault currents to return to the source. This helps to quickly trip over current protection devices, such as circuit breakers or fuses, and energize the circuit, reducing the risk of electrical shock and fire hazards. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, as specified in the National Electrical Code. It is crucial to select the correct size of grounding electrode conductor to ensure that it can effectively carry fault currents. The grounding electrode conductor must be connected to a grounding electrode, which can be a ground rod, a metal water pipe, or a concrete encased electrode. The grounding electrode provides a connection to the earth, which helps to stabilize the voltage of the electrical system and provide a path for fault currents to dissipate. The grounding electrode conductor must be installed in a continuous length, without any splices or joints except for irreversible connections made with listed connectors. This ensures that the grounding electrode conductor provides a reliable path for fault currents. The grounding electrode conductor must be protected from physical damage and corrosion. This can be achieved by installing it in conduit or by using corrosion-resistant materials. Proper installation and maintenance of the grounding electrode conductor are essential for electrical safety. It is important to regularly inspect the grounding electrode conductor for damage and corrosion and to ensure that it is properly connected to the grounding electrode. Bonding is another important aspect of electrical safety. Bonding is a connection of all non-current carrying metal parts of an electrical system to create a low impedance path for fault currents. This helps to prevent voltage differences between metal parts, which can cause electrical shock. Bonding conductors must be sized according to the requirements of the National Electrical Code. It is important to select the correct size of bonding conductors to ensure that they can effectively carry fault currents. Bonding conductors must be installed in a continuous length, without any splices or joints, except for reversible connections made with listed connectors. This ensures that the bonding conductors provide a reliable path for fault currents. Bonding conductors must be protected from physical damage and corrosion. This can be achieved by installing them in conduit or by using corrosion-resistant materials. Proper installation and maintenance of bonding conductors are essential for electrical safety. It is important to regularly inspect the bonding conductors for damage and corrosion and to ensure that they are properly connected to the metal parts of the electrical system.